So welcome to the first lecture of quantum field theory. So before we actually get into quantum field theory, we shall need to review a few background material. So in today's lecture, we are going to review special relativity. So as the name suggests, this will be a review, although logically it'll be independent or it'll be self-contained, but it'll help you if you have seen some of this stuff before. So let's begin with the two axioms for special relativity, or let's say two postulates. The laws of physics are the same in all inertial frames. So let me remind you what an inertial frame is. An inertial frame is a frame of reference in which if a body is in motion, it continues in a straight line unless there is some external force acting on it. So this is something that we also have in common with Newtonian physics. But in special relativity, we have a second postulate. And the second postulate is that the maximum speed with which signal propagates is the same in all inertial frames. So usually this is formulated in terms of the speed of light. And the thing is that light being made out of particles which are massless do propagate at the maximum speed possible. Therefore, sometimes we'll see the second postulate saying that the speed of light is the same in all inertial reference frames. So the first postulate is true of Newtonian physics, but this is also known as Galilean relativity, because Galileo was the first one who formulated this principle. But these two postulates together form what is called Einstein's special theory of relativity. As the name suggests, there is also a general theory of relativity, but that is for another day. So what is Galilean relativity? So in Galilean relativity, if we have 2 points whose spatial coordinates are the same in one reference frame, in one inertial reference frame, their spatial coordinates may not be the same in another inertial reference frame. So for example, suppose we have some coordinate system. So here, time flows in the upward direction, and here we have x and y. And suppose there are 2 points, say P, at some time, and another point later, Q. Now in this reference frame, they have, P and Q have the same spatial coordinates, although their time coordinates are different. Now suppose that we have another reference frame. Let's use dashed line for that. Suppose we have another reference frame. And suppose this reference frame is moving with respect to the first reference frame in that direction, in the y direction with some velocity v. So this is, say, t prime, this is x prime, say this is y prime. We see that in this prime reference frame, says the prime reference frame coincides with the unprime reference frame at, say, t is equal to t prime equals to 0. So we see that at that time, the point P will have some, some coordinate, which is say x prime, y prime, and also probably z prime, although we have not shown z prime there. So the point Q, which is going to be at a later time, is going to have a different spatial coordinate in the prime frame. So if this is say x, y, and z, that will have say x1 prime, say y1 prime, z1 prime. So we see that in the prime reference frame, P and Q, they don't have the same spatial coordinates. So this is what is meant by Galilean relativity. If we look at the time that has elapsed between these 2 points, P and Q, in the unprimed frame, that's going to be delta t. And the time that has elapsed in the prime frame between these two, and let's call that delta t prime, those two are going to be the same. So in Galilean relativity, we say that time is absolute, meaning that the time coordinate is the same, or the time that the time flows at the same rate in all reference frames. But we saw that the spatial coordinates need not be the same. However, we shall see that these things are not true in special relativity. So before we do that, let me introduce a concept. The concept is an event. So what is an event? So an event is a point in space-time, and it is characterized by 4 numbers in some inertial reference frame. So suppose that we have space-time here. So suppose this is the spatial direction, this could be more than one, and this is time direction. An event is just a point in space-time. So it'll have some time coordinates, say t1. So let's call this event number 1. It'll have some spatial point like x1, y1, z1. And then this could be another event 2, and this could have coordinates t2, x2, y2, z2. So that's very simple enough. Now, in Galilean relativity, if we take, say, if we go back to this picture, if we take 2 events, say P and say R, and then P and R, we see that P and R occurred at the same time. So in the unprimed coordinate system, the time coordinate of P and the time coordinate of R are the same. If that is the case, then we see that prime coordinate, the time coordinate of P and the time coordinate of R is also going to be the same. So in other words, the time coordinate, that if 2 events are simultaneous in the unprimed coordinates, they are simultaneous in the prime coordinates. So let's write that down. So, so this is what we really mean by absolute time in Galilean relativity. And now let's see what happens in special relativity, Einstein's special relativity. So to see this, let's consider 2 reference frames. And now we are not going to draw the time, but just the spatial axes. So that was Z, and this is X, and say this is Y. So X, Y, Z. I'm not caring about left-handed and right-handed stuff. And suppose there's another coordinate system, which is moving with respect to this first coordinate system, and that is the green coordinate system, and this is, or the primed coordinate system, let's call it primed. And suppose there are 3 points in the prime coordinate system that are stationary in that system. So A, and there we have, say, B, and here we have C. So these are, A, B, C are stationary in the green or the prime coordinate system. And the prime coordinate system is moving with respect to the unprimed coordinate system with some velocity, v, along the x-axis. So now suppose that at some point, a flash of light emanates from the point A. So at some point, A gives out a flash of light. And it, spreads out. Now, if I look at this in the prime coordinate system, because B and C are equidistant from A, and the flash of light reaches B at the time that the flash of light takes to reach B is the same as the time it takes to reach C. So delta AB, or let's call it delta T, AB is going to be equal to delta, say, T prime of AC. We are using prime because we are in the prime coordinate system. Now let's look at it from the unprimed coordinate system. In the unprimed coordinate system, all these 3 points are moving in that direction. And therefore, after the flash of light, starts its journey from the point A, before it reaches either B or C, the point B has moved towards the source and the point C has moved away from the source. But according to the special theory of relativity, the speed with which the light travels in the direction of B and the speed at which the light travels in the direction of C is the same. But because B is moving towards A, the light has to cover less distance. And because C is moving away from A, the light has to cover a longer distance. So in the unprimed coordinate system, the time that the flash of light takes to go from A to B will be less than the time that the flash of light takes to go from A to C. And thus we see that 2 events, meaning that the events of the flash of light reaching B and C, those 2 events are simultaneous in the reference frame, that is the prime reference frame, but they're not simultaneous in the unprime reference frame. So we see that the notion of simultaneity is no longer an absolute concept. This doesn't mean that the notion of causality is breaking down. As we shall see, there is a very well-defined causal structure in special relativity, but the notion that 2 things has happened at the same time depends on the observer. So I want to now give you an exercise, and I strongly encourage you to do this at home. So the exercise is that repeat the thought experiments that we did here, this experiment, for Newtonian or Galilean relativity. Okay, repeat the thought experiment for Newtonian or Galilean relativity. Now you can do it in two ways. First, assume that the speed of signal propagation is infinite. The other one is to assume that there's a preferred reference frame. So for example, there is some sort of medium in which your system is embedded, and the propagation velocity or speed is given for that medium. It's like suppose that the two things are communicating by some sort of sound wave. Then of course the velocity of that wave will be different in different reference frames. So by adopting each of these assumptions, you can show that in Galilean or Newtonian relativity, simultaneously is an absolute concept. All right. So another important concept that we will need for relativity is the idea of an interval. So what are intervals? Intervals are essentially a generalization of the distance. So intervals are the correct measure of distance between two events in Einstein's relativity. So what do I mean by that? So instead of saying from now on that the maximum allowed speed of signal, we're just going to use the speed of light. So the speed of light is an important concept, an important constant, and its value in the MK system is given by 2.9972458 into 10 to the power 8 meter per second. Now this is actually an exact number because it turns out that this is actually the definition of a meter. So now suppose that like a pulse of light emanates from some event, which is given by say T1, X1, Y1, and Z1, and it reaches some other event, say T2, X2, Y2, and Z2. Then what is the distance that the pulse of light travels from point 1 to point 2? Well, it's given by the speed of light times the time interval, which is T2 minus T1. But we know that that distance is equal to the distance between the spatial points. So that should be equal to square root of x1 minus x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. So in other words, if you square this is c squared, t2 minus t1 squared, and that's equal to, I'm just going to do a shortcut. This is an equality we get. Now let's look at the same two events in a different reference frame. So in a different reference frame, point 1 will have, say, some coordinates at t1, x1 prime, y1 prime, z1 prime, and point 2 will have coordinates t2 prime, x2 prime, y2 prime, z2 prime. And the analogous relationship then would be c squared t2 minus t1 primed squared is equal to x1 prime minus x2 prime whole squared plus y1 minus y2 primed squared plus z1 prime minus z2 prime squared. So now what we're going to do is that we are now going to define something called an interval between any two events. So given any two events, not just the events we're discussing, 1 and 2, the interval between them is defined by this formula. So this is the interval, and the interval is equal to the square root of this thing, c squared t2 minus t1 squared minus this thing, x1 minus x2 whole squared minus y1 minus y2 whole squared minus z1 minus z2 whole squared. Notice that over here we have the plus sign, and here in front of the spatial parts we have minus signs. So this is the interval. So then we can have the interval. So for the unprimed coordinates and unprimed reference frame, as well as the interval for the primed reference frame. And for the points that for the two events that we are discussing here, 1 and 2, what we are seeing is that this formula is telling me that S12 for these points is equal to 0. And also what this is telling us is that S prime 1, 2 is also 0. In other words, for these 2 points, which are light-like separated, so 1 and 2 are light-like separated, meaning that one event can be reached from the other by a beam of light. We see that the interval does not change, and it is actually 0.